Hello, and welcome back to another episode of Quarks and Quarter Notes. Today, Tyler and I will be discussing the James Webb Telescope, the Hubble Space Telescope, as well as speculation on things like alien life and cosmology and some other fun stuff. As always, if you enjoy the podcast, be sure to like, comment, subscribe on whatever platform you're on, as well as share with those who you know may enjoy it. So 30 years ago, we had a much more vague notion of how the universe was. I think it was only 10 or 20 years ago that we actually discovered things were accelerating because of Hubble.
Yes, it was observation of supernova that let us understand that it was accelerating.
I know water vapor on Europa, tons of other stuff. And it's like, that's about to happen again. We have some idea of the kinds of things we're looking for, but there's really no telling what we're going to see. And that's amazing.
It's exciting, right? It's just like, well, when we put Hubble out there, we didn't know. How would you predict of like the deep field image that it produced? Like that's crazy.
Yeah. Okay, well, how about this? How about we work our way to it? So, how do we get to Webb? So, we start with our eyes, right? And we can just look up and we can see like points of light for the stars. And
We did that for a long time.
What happens after that?
It would be Galileo, right? I don't know when the first telescope was made, but isn't he about that time-ish? And then the telescope, like, it let us see better resolution of the planets and stuff in our own solar system. But for pretty much anything outside the solar system, a telescope like that won't do a whole lot for you.
And that was a huge leap. Even still, even though you can't see outside the solar system, but without a telescope, you don't really know what Jupiter looks like. It just looks
Right.
like a little glowing
Well,
dot.
it's the same as like any other star in the sky, right? It's just a weird moving one.
Yeah, and that's where the word planet comes from. I believe it's wanderer in Greek, because they were the stars that moved around.
They had a weird pattern in the sky. Instead of just going like across the sky as you would expect it to go every day. Had a weird path.
And people like Galileo built their telescopes, and they took a look at the skies, and they saw that they weren't just little like moving points of light. They were actually planets, not unlike our own. That was a huge deal.
Oh yeah, I mean we got like Kepler's laws of motion from those observations.
It's a sort of a pattern of things where we think something's unique, and then we look out and we discover it's not unique.
Right.
We think the Earth is special and there are all these little points of light,
Mhm.
and then we look out and we're like, oh wait, there are other things like this.
Yeah, I mean we started with a Earth-centric view of the universe, right? And then we learned that it's not Earth that's at the center of the universe, it's actually the sun that's at the center of the universe. And then we kept learning, it's wait, hold on, the sun's not even at the center. Like the sun's just this part of a collection. Develop it, what's it called? The Anthropic Principle? Is that what we call it nowadays?
Well, the Anthropic Principle is the idea, I've always heard it explained in the sense that there are many areas of space with different laws and different environments and things like that. And even if it's incredibly rare, well, it has to be possible because we're here. So we're the spot where it actually happened and where it had to happen, and everywhere else. We're not lucky, but we're necessary, if that makes sense.
Oh yeah, no.
I don't know if...
The places you expect to find life are places where life can form.
Yeah, that's...
Right. Well,
it sounds funny, but...
I was just thinking, maybe it's not anthropic, but like the idea that astronomy in general has taught us that the more we learn about the universe, the less special our particular place in it is, if that makes any sense.
Yeah. So we started with that, and we found we had more planets. But then it's like, okay, so there are other planets, but we're here in our solar system, and we have the sun, and we're going around it with these other planets. We eventually came around to that, but like that's it. The story kind of ended there, and then you have those other little stars, points of light, which supposedly distinct from the sun.
They seem pretty distinct. The sun's pretty bright. That's quite an intimidating force.
So, what was the next step from just like Galileo's telescope?
Well, it would probably be Hubble, or about Hubble's time, is
Right. So we built bigger and bigger telescopes.
essentially right.
And this isn't to be confused with Hubble's telescope, right? Because
Yeah,
Hubble himself,
right.
he didn't use his
No,
telescope.
no. But yeah, he was just using observations of just whatever instruments they had back then.
Yeah, the really powerful telescopes. I think he worked at an observatory. So he looked out with his telescope, and similar to the discovery of other planets, he discovered that there were actually other galaxies.
So there was like a cluster of stars in the sky, and we were using methods to figure out distances, just using luminosity relationships and such.
But like, they
Yeah.
didn't think they were other galaxies. They thought these were just other stellar objects,
In our galaxy. Yeah.
like clouds of
Yeah,
dust.
like clouds,
Yeah,
just big clouds of dust, like somewhere in the galaxy, which at the
right.
time was the universe, essentially.
The galaxy was the universe.
Mhm.
Yeah.
And then we made observations, and we were looking at like a cluster of stars. And whenever we tried to figure out how far away it was like way further than anything else we've observed, just like by many factors. And we're just like, maybe it's a completely separate. And they called it an island universe, is what they named the first galaxies, because they were just like little islands of stars that were just super, super far distant from each other. And so I guess Hubble is the next big leap in the universe we could see.
And there's sort of a diminishing return on building bigger and bigger telescopes, as far as I understand it. So we have an incredibly massive telescopes here on Earth, but it's like at the point we're at, you could double, triple, quadruple the size and barely get any kind of return.
The atmosphere is really the biggest issue.
I know light pollution's another factor. So like, I mean, when you're in the city, you look up, you might see a handful of stars, but when you go out into the country away from those lights, you could see enormous amount of stars. And the farther out you get from society, the better and better
Right,
things start
that's
to look,
true.
and the more things you can see.
Telescopes are generally high up, so there's less atmosphere, and then far away from cities. Those are generally the
Yeah,
best
and I know
spots.
some observatories actually have deals with cities where they use specific types of street lamps and stuff to minimize
Mhm.
light pollution.
Especially at McDonald Observatory. They work with the nearby cities to do special street lamps and special kinds of paint, I guess, on the road or whatever to absorb light a little bit better. The telescopes are extremely sensitive to anything. It's crazy.
Yeah. So between the light pollution and the atmosphere, the next step from building a bigger and bigger telescope would be putting it away from these factors which make it more difficult to see. So yeah, in the 90s we launched it. It's not working.
Yeah.
Takes a few years to get it like fully functional, but once it's functional, my goodness. Have you I'm sure you've seen maybe every major picture, but man, I'm looking at some right now,
hmm
and
Like of different
it
nebulae and just,
it blows
it's
my
crazy.
mind. The pillars of
hmm
creation, the Eagle Nebula, the deep field, of course.
The deep field image is my favorite image.
It's incredible. Do you want to just explain real quick?
So, from what I understand, the deep field image didn't come out until a few years after Hubble had been looking at different things in the sky.
Yeah, like 14 years, quite a
Yeah,
bit.
so it had done quite a lot of it. Because, of course, anytime a new telescope goes and comes up, all scientists are looking like they want their telescope time to look at whatever research
Yeah.
they happen to be working on at the time, because that's what's important. Hubble had been up for, like you said, 14 years. The director of the telescope said to point it at the darkest spot in the sky, essentially. And it's a little square. The area of the square is about a tenth of the size of a full moon. So a really, really tiny portion of the sky. And it was the darkest part of the sky that we knew about. And so we just like kind of let it stare at it for a few days. And then what came out of it was a picture with tens of thousands of galaxies in an image. Something that was completely unprecedented and unexpected, I would say.
Really incredible. And also the farthest we've ever actually looked.
Yeah, I mean, there's a hard limit when it comes to visible light. Even with Hubble, it could stare at one spot in the sky and just collect light for, I mean, like years. But there's a hard limit to how far visible light has traveled to us.
Yeah. So we know light takes time to travel, takes time to travel from me to you if we're standing in front of each other. It takes time to travel from the sun, about 8 minutes, and farther ways, longer and longer. So, like that deep field image, we're looking billions of years for that light. We know that's how long that light has to take to get to us.
Right.
So we're looking into the past.
Essentially, any time you're looking out, you are looking into the past. Yep. You're
Right.
seeing things as they were.
And with Hubble, the ultra deep field, it's like a time machine at the same time. It's literally, we're looking at the beginning of the universe.
Yes, it's a screen to the past, like literally.
And it has to be that way.
Well, I wouldn't say it has to be that way. I would say it is that way. I don't think anything would necessitate it, do you?
Well, it's like, how do I say this? We can look into the past in a lot of ways. We can like look at fossils and we can read historical accounts and things like that. But there's always like some data lost there, and
because it's like pseudo looking in the past, right? We're looking at it in the present.
And there's always lots of room for things like contamination and for mistakes and stuff. And of course, over lots of time and lots of samples, we work down relatively accurate accounts of the past. But with this, as far as everything we understand, there's really no room for any error. Like we're looking at the past,
right, as it was,
to a huge degree,
right,
as it was, yeah, with no room for error, really.
And the Big Bang Theory, which is our current theory, best theory of cosmology we have that describes the universe and its evolution, is an observational one. It wasn't one that was like built up a priori from like first principles or something. We looked out, we saw what the universe was doing, and we were just like, okay, we wrote that down.
Yeah, I think that's what I'm trying to get at, is that we can literally just look.
Yes.
And it's right there in front of us. And that's so bizarre to me.
It is.
It's as certain as you can be about anything.
Right. Anytime I go outside, like at night or whatever, and there's just a bunch of stars and I look up, I'm just, in my mind, I'm like, that's literally infinity right there. It's like, it's right there above my head, infinity. Like,
and it's like, because of the way time works, how relativity works, if right now, I'm saying now in air quotes because now doesn't really make sense when we're talking about it like this, if there's someone else over there in that area that we're looking at, they would look back at us and they would see what we see, like this early formation of the universe. But there could be countless civilizations over there that
exactly.
That is really crazy. So all of that's just Hubble. We haven't even talked about Webb. So why don't we talk about James Webb?
James Webb, the telescope, or the person.
Yeah,
I don't know much about the person, I'm gonna be honest.
Yeah, well, I looked up. I've known about James Webb for a long time. It actually is as old as you and I. They started the project in '95.
Yep.
When we were born. Yep. We've kind of grown up with it.
It was supposed to take like 10 years and a few $100 million. Was the James Webb Telescope project. They're about 15 years overdue and about $9 billion over.
So I've known about the telescope since high school for quite a while now, but it wasn't until maybe a few months ago that I actually was like, who's James Webb? So I did look that up, and he was the director of NASA during the Apollo missions, so he was a big part of that. But outside of that, what is this and why is it special?
The James Webb Telescope is essentially, we would just call it the predecessor to the Hubble. It has a much larger mirror, so essentially a bigger eye to see. And it's looking at slightly different wavelengths than Hubble. Hubble looks in the visible spectrum, so it looks at light that you or I can see. James Webb, the light that it looks at will be red and infrared, near infrared light. So really low energy, high wavelength light.
So light that we experience, but we can't see it because it's not in the right wavelength of our light. Unless we put on, like heat vision goggles.
Right. But even, right. What heat vision goggles does is it sees the infrared and then it turns it into visible light you can see.
Yeah,
Right.
that's for, let me think. So for those who aren't like super familiar with all these terms, infrared is, we can't see it, like you say, it's not the right frequency, but we can experience it as heat.
Right. Well, one way I kind of like to think about it, when we're looking at a rainbow, right? On a rainbow, you have like a red side and a purple side. And we see this rainbow as like a band. That band doesn't necessarily end. On the red side, it keeps getting redder and redder and redder and keeps turning into more colors that we can't see. And same on the blue side, it keeps getting bluer and more purple and bluer and bluer. And
Right.
like that light still exists in those wavelengths. We just don't see it. And
We don't see it, but we can feel it. um, so actually, you can do an experiment for this yourself by throwing light through a prism, and you can put a thermometer. So you can find purple and go all the way to red. You can put a thermometer just outside of red, and you can put a thermometer on the other side of the room. And the thermometer just outside of red, you will get a slightly higher reading as it picks up that infrared light.
right. That's very interesting to me because red light is lower energy, but I guess it like absorbs better or something and causes it to heat up easier.
I'm not sure the mechanics behind that, but
I have no idea.
yeah, I don't know. But that's how like heat vision works and such. So
Well, like we
yeah,
were talking
I don't know.
about in our astrophysics episode, anything with a temperature will emit
Right.
infrared light.
So why is it significant that it's looking with infrared as opposed to visible light?
One significant aspect of infrared is that we were talking about how light travels from the sun to the earth. It takes the light about 8 minutes to travel, and like sun to the nearest star would take about 4 years for light to travel from there. In terms of the universe is big even for light. It takes a long time for light to go through it because it is truly quite immense. And it's expanding. And so, what this actually does to light, this doesn't happen to normal matter. If you have normal matter in a space that is expanding, you just have that clump of matter that just kind of stays there. But if you have light propagating through space and you're expanding, what you're doing is also expanding the light, and that correlates to making it lower and lower energy, which we would say would be getting redder and redder, a process known as redshifting. And so what happens is, I said earlier there was a hard limit on how far out Hubble can see with visible light, because the light coming in, eventually it'll get stretched out of the visible range into the infrared. And that limit of getting stretched from visible to infrared, that's as far as Hubble can see. Does that make sense?
Yeah, so it's sort of akin, sort of. It's not quite the same thing, but it is a bit like what you see in superhero movies where you have like a speedster who runs so fast that eventually they get to a speed where you literally can't even see them. And there's sort of an analogy there where the universe is, the things farthest away from us are moving away faster and faster,
Right.
and eventually we can't see them because they're moving so
The
fast.
things furthest away, their light has been redshifted more and more into the infrared, and so James Webb lets us see things that are even further away than what Hubble could.
Yeah, I actually looked this up in preparation. So Hubble in the deep field, we're able to see about 400 million years after what we believe the date is for the Big Bang, which is pretty, considering that's like 13 billion years in the past, basically. So James Webb won't be able to see like billions of years closer, but it will be able to see within 100 million years of the proposed date for the Big Bang. So that's 300 million years of history of the early universe at our disposal.
And what's interesting is there's a gap too, because we've mapped out the radio signals from the universe, the cosmic microwave.
Background radiation.
Yeah. So what that is essentially the early universe, all the matter and energy in the universe started out really close to each other, or really close and really dense. And as it started expanding out, there was a time where photons were decoupled from the matter. Essentially, they were allowed to propagate, because before you couldn't, a photon literally couldn't move. There was just too much stuff in the way. But as the universe expanded, the photons became decoupled from the matter and are able to propagate through. And that is the earliest, that's a hard cap on what light can give us as far as a history of the universe. And that light has been redshifted into the radio wave. So it has been redshifted an enormous amount. So there's like the radio waves that let us see as far back as 300,000 years after the Big Bang is the radio light. And then the Hubble images, like you said, let us see hundreds of millions of years afterwards.
Yeah, 400 million.
Right. And then James Webb is going to fill that gap.
Yeah, at least a big part of it.
Right.
And there's just no telling what we're going to learn, right? Like
right. I feel like a lot, so there is a lot of what James Webb will see ideally will be a lot of confirmations. It'll just be a lot of confirming theories that we're pretty sure of. Most ideal situation is that it sees just something we can't predict. Who knows what's out there in the universe? That would be amazing. It'd just see something totally unprecedented that you couldn't it sees dark energy or something weird.
Yeah, it's hard to predict what we could see that we wouldn't be able to predict, you know?
Right, exactly.
Like,
there's no way you could have made a prediction of the deep field image with tens of thousands of galaxies in a tiny little area of the sky. You don't be like, well, when we put Hubble up there, what do you predict? Do you think there's going to be a tiny patch in the sky with tens of thousands of galaxies in it? It's like, no, you don't make that prediction.
Equivalent would be like we see tons of other universes with different physical laws, you know, like
we just see something weird. Yeah.
Something really just that we couldn't really expect. So that'd be cool. But we also would be cool if nothing else to confirm our theories, to confirm that the laws of physics, for example, were the same then as they are now. There's no reason for them to be different, but it'd be great to just, you know, reinforce that. But yeah, so that's just one little aspect of the telescope. That's the other thing about infrared, I guess. It's better at detecting planets, am I right?
Right. So there's two things that James Webb will be looking at primarily. The first thing would be very, very distant objects, early galaxy formations and such. The other thing that James Webb will be looking at primarily is other planets. From what I understand, we're trying to get signatures of types of gases in other planets because all stars essentially are emitting light, obviously. And as a planet orbits the star and like it comes in between us and the star, that light will filter through the air and the atmosphere of that planet. We will see like dips in the normal light curve, and that those dips correspond to different elements in that the light had to filter through.
It's like waiting for an eclipse, right? So it'd be like us waiting for a lunar eclipse to read some things about the moon, and if the moon had an atmosphere, figuring out what the atmosphere was by how the light filtered through the edges.
Right, exactly. If the moon had an atmosphere.
If the moon had an atmosphere, yeah. So the James Webb will be the Earth, and then the moon will be the planet, and then the sun will be the other star.
Right.
In that analogy. Right. And apparently that's going to give us a lot more information than we currently can get now, because you can really get only so much with just visible light.
Oh yeah, there's a huge limit.
Why are you interested in seeing other atmospheres?
Well, tinfoil hat time. I'm interested because aliens, essentially. If we see really weird signatures, very complex molecules, or things that shouldn't really be there, that would be very interesting, I think.
Yeah. So one thing I recently read, if we discovered oxygen, for example, on another planet's atmosphere, oxygen is highly reactive. It will basically instantly react with anything. So if we found an atmosphere that had oxygen, that would mean something would need to be producing oxygen. And right now, the only thing we know of that produces oxygen is life as we know it.
Yeah, oxygen is a very clear example because, like you said, it reacts. If we saw an Earth-like atmosphere, we have mostly nitrogen and then a little bit of oxygen, essentially, and then some other stuff, but it's mostly nitrogen and oxygen. That would be a very strange thing to see on another planet, right? Or even
Yeah, I think if that happened, I feel like we could only reasonably assume that there was life. I mean, that would be the best guess.
well, we would like increase our credences for there being life, right? It would definitely.
Well, it wouldn't have to be life.
Right.
We could
Yeah.
discover something else,
some
that
other
produces that
mechanism,
kind of atmosphere.
geological mechanism that we're just not aware of because we have Earth geology, but
Yeah, you have to leave room for
Right.
that. But given what we do know, that would be our best guess. And the fact that we could soon be in a situation where our best guess would be something like that is pretty exciting.
right, or just not even oxygen, but just like really complex molecules. Think of like molecules from factories here on Earth that we use to produce certain materials.
Yeah.
The exhaust gases and such are really, really complex, not something that would be made from normal geological processes as we know them.
Some of the heavier elements that we've been able to synthesize but don't occur in nature.
Right, exactly.
As far as we know.
Exactly.
Yeah, lots of really cool potentials. And even just like excess infrared heat, like just population explosions create lots of waste heat.
Right. I imagine that'll get kind of drowned out by the local star, but you never know.
Well, if not, the civilization's big enough,
Right. If they're consuming stellar amounts of energy, sure, yeah.
Yeah, exactly. That's what I'm thinking. So why don't we make the case for alien life real quick, just for funsies?
The best case I think for it is just the sheer size of the universe. Like the universe is really, really big, and to assume that we're like a fluke of some sorts, that would be really strange. We'd be quite the fluke. And
well, to elaborate that in more detail, like you and I, we are made of particles, and you can zoom in and you can see all these particles. You can see how they're arranged, and you could describe everything about you and me in terms of the particles we're made out of. And there are only so many ways you can organize particles.
Right. That number is very large, but finite.
Yeah, it is very large. But it is finite, exactly. Right. So in a big enough finite universe or an infinite universe, there's no way around it not happening.
Right, exactly. My suspicion is that life is pretty common throughout the universe. I expect, I don't know to what degree. I don't expect it to be rare. I don't know if every single solar system has life on it to some degree, or maybe it's like every million solar systems.
We could say it's incredibly rare.
Right. But I expect it to be, I expect the universe to be pretty much full of life.
Yeah. So what are your responses to something like the Fermi Paradox, which is to say, if life should be so prolific, why haven't we encountered it yet? What's your thought?
Well, the first thing is, like I said, space is big. Perhaps too big to get across easily. As easy as perhaps the Fermi Paradox is like asserting that, like, if we're a sufficiently advanced technology, we can go from one side of the galaxy to the other. Perhaps just way harder than. And then there's other like great filter arguments, I would suppose that.
Well, like what are the most convincing ones to you? Would you say that just the pure distance is really the thing that?
Right, and if we're looking at, so like another response to the Fermi Paradox, I think, is the slice of time that we've been looking out at the sky with these advanced telescopes and with a better scientific understanding of the world and such. That slice of time we've been looking at is just like we've looked at the sky and then we stop looking, like, essentially, like, and it's like, oh, we didn't see anything, and it's like,
it's very hard to understand. That's actually, so that's my favorite objection. I'm not as, I don't love the things are too far objection, because if you think about, like, the Earth's been around for what, 3 billion, 4 billion years, something like that. Yeah, and the universe, 13 billion. That's a lot of time. And if any other civilizations happened, could you just imagine if we progress from where we're at for, forget just like hundreds and thousands, but millions and billions of years?
yeah,
That's hard. I can't imagine it.
right,
I literally can't imagine
right,
it. But what I would guess is that with that amount of time, you would find a way to traverse the universe,
right. Well, that's if there is a
effectively.
way to.
If there is a way to. So yeah, but I'm not super convinced. But I do think that that second one, the objection that we just haven't really looked,
Yeah,
is pretty apt. If you just how big and like you said, the time slice. So you have to combine the very little bit we've actually been able to look with the very short time.
right,
The analogy I like is that it's like looking for whales in the ocean and like taking a one cup and
right.
just like scooping it up and like,
Nope,
nope,
no
no
whales in
whales.
here. Yeah. You could, yeah, that's exactly it. That's my biggest objection to the Fermi paradox.
Yeah, I think so too. And this James Webb, it's sort of like taking a slightly larger net. Still might not find whales, but maybe it'll get caught on a tail or something, you know?
Right. Something, it'll see something.
It's crazy to think that there might be other life, might be life out there, and it's also crazy to think we might be the only ones. They're both just very difficult to think about.
Right. They would both be absurd either which way.
Yeah. I am on the same page though as you. I think it's quite likely, even if it's incredibly like one of the most rare, even if it's the most rare phenomenon in the universe, it has to happen more than once.
Right, exactly. Because even something that only happens 0.001% of the time, that happens all the time here on Earth. Like people win jackpot lotteries and stuff. Like those are tiny, tiny chances. We haven't even gone past the Earth, and we're already hitting these tiny, tiny probabilities. So to imagine all those probabilities scattered throughout the universe is just like, yeah, there's no way we're the only life.
It'd be a very bad bet.
Yeah.
The which objection? What was the other objection you mentioned? I just want
To the Fermi
to mention it.
paradox? Oh,
Yeah,
it's just that.
the extinction or
Oh, just like great filters. The idea that, so if you do imagine we keep getting more and more advanced right now, past what we are, we're capable of nuclear technology. Just as a reminder, that's literally the power of stars in some sense that we understand to some degree. Future technologies, if they we just keep getting more and more advanced, it'll be more and more dangerous, essentially, right?
instead of harnessing the power of the sun, maybe we harness the power of a black hole
There's something
or something.
strange or just right. And it just, there's added risk each time you're dealing with these insane energy scales. And so there's just ideas of like great filters that as life becomes too advanced, it just like kills itself because you're just dealing with these crazy huge energy sources and whatever.
We flip on the engine to do our interstellar travel, but
And it just
we
creates a
over
black hole.
a black hole and
Yeah,
we all
that's the end
perish.
of that. Right. Like, who
I'm
knows?
that it's very possible. I think that objection is pretty reasonable, but I'm more optimistic than that, I think.
Well, it's
Um,
these ideas of, it's closely tied to these ideas of like levels of civilization, where like a type 1 civilization has like full control over its planet and it can essentially harness all of the planet's resources and leverage them in some sort of way. Then a type 2 planet would be able to leverage the energy output of its nearby star or perhaps few stars, and then a galactic civilization would be able to make use of an entire galaxy's worth of energy of some sorts. And I think the great filter is what prevents these huge galactic civilizations from happening. I don't know exactly what the filter is. It just seems like reasonable to perhaps expect some sort of like check that nature does.
if that were the case, we would expect to maybe be able to find other life, but it wouldn't be galactic scale crazy civilization. It might be, I mean, you could even think of like other humanoids. You could think of like, I mean, us, for example, but also us like 100 or 1,000 years ago, like maybe there's a bunch of ancient Roman civilization scattered
Right,
out.
exactly. And I mean,
They haven't built radios yet.
They could be like extremely common, right, and be everywhere. They're just not going to be traversing the universe just because.
Or sending out radio signals.
Right, exactly. Or anything of that sorts.
And that's so that what's interesting is if that argument is true, it still would allow us to like say detect an Earth-like atmosphere with the James Webb.
Yeah.
Find life there, but and if anything, that might be a cause for concern.
Well, yeah. Well, I mean,
I think
we're trying to get onto Mars right now, so we have people working on that issue sort of a little bit.
Well, but I think given that we are relatively new in the universe, all things considered, if we found life less advanced than us, I think I would be a little bit more concerned about the filter. But, I'm still an optimist at heart, I think. I would give that argument a little bit more weight, though.
Give it a little bit more credence. Well, even like, I expect life to be common. I don't know if like super intelligent life that's able to like change its environment in extremely significant ways. I don't know if that kind of life will be common. But just like
not
things
common,
things that like move around essentially is what I mean by life. Like made up of particles, protons and neutrons and electrons, like just
and replicate themselves. Yeah. I think that's sort of one of the requirements is you have to be able to replicate yourself with some fidelity, like maintaining some sort of
I don't know. Well, that's how we do it here on Earth. Maybe other life just lives along.
Oh, like they're just born and then they live forever?
Yeah.
And that's,
or they just live for like a long develop their next life or whatever it is. I don't know. I'm open to possibilities. Is all I'm saying.
Well, yeah, there are other proposed types of life, so carbon is us, but I've seen some pretty compelling theories for silicon-based life.
Silicon, that would make sense. Well, carbon just makes sense because carbon as a base for a molecule can create
that works with everything.
Can create more molecules than all other elements as bases for molecules combined. Right. Like carbon it's an excellent base molecule to start out with. So I would not be surprised if there's other carbon-based life forms. I mean, even on Earth, the distribution of life with a carbon base, right? Like we have humans and we have octopuses and we have like bumblebees and birds and like it's all based on carbon, right? So like even on Earth there's a huge variety, so I could expect a even larger variety of carbon based, or like you said, even silicon based, whatever kind of life that would mean.
Star Trek had a pretty interesting episode. I mean, obviously it's sci-fi, but it had an interesting episode where they had some silicon based life and it propagated itself like through rocks instead of through air, and that's a pretty interesting idea. It's not also just that the universe is big, but the stuff we're made out of is pretty common.
Yeah, it's everywhere.
The top elements that we're made out of: oxygen, carbon, hydrogen, and nitrogen. I'm not gonna look it up, but I have a feeling if I look up the top 4 most common elements in the universe, I think 3 of them are going to be there.
Well, hydrogen for sure. That's the most common. Almost the entire universe is hydrogen by mass.
It's one of the things that makes up most of our body. I think it's the second next to oxygen.
Carbon. Well, that makes sense because those are the elements that are able to be made inside of stars without like supernova explosion. Like our sun can create carbon, I believe. It won't be able to, like once it gets up to iron, once it gets up to iron, like it can't make those elements.
Not even is the universe so massive, but everything that you need to make us
it's not
exactly what the universe is.
There's a lot
it's everywhere.
Yeah. The ingredients for life seem to be everywhere. I would say that.
Yeah. Littered.
I would say you probably need some sort of solvent and just like energy. Some sort of energy source and some sort of solvent for chemistry to start happening.
Yeah, you need like you need either a star or like a hot core of a planet or asteroid or
Yeah, some
something.
sort of
Yeah.
something.
So yeah. So James Webb launched and is going to uncover some of that. What's this Lagrangian thing? You want to explain that to me? I remember when we talked with Karamvir about the moon stuff. He talked. You guys talked a little bit about
Lagrange
Lagrangian.
points. Oh, we were
math.
talking about Lagrangian mechanics, which are that's a way separate thing. Lagrange was a smart
Okay,
dude. He
does that have nothing to do with
nothing
this?
at all. The only thing that's related is that it's Lagrange. Yeah, Lagrange mechanics are talking about it's like F equals ma type stuff, trajectories of objects. Lagrange points are so whenever you have a two body system with gravity as its main function that's keeping them close together,
like a planet and a moon.
like planet and a moon. There's always going to be 5 Lagrange points, is what we call them, and they're essentially points where the gravity of both the planet and the moon, they kind of equal out on each other. They work with each other in some way that makes that particular point of like stronger in gravity, I guess you could say.
Okay, so they're points in between bodies or around bodies where they have like an equal pull.
Yeah, the gravity kind of conspires.
So where it's like kind of stabilized.
Right, exactly. So the Lagrange point that James Webb is going to go to. So we're using the Sun Earth as the two body orbit, or as the two body system, the Sun and the Earth. It'll be going past Earth. So if you draw a line from the Sun to Earth and you keep going a little bit, that's where that will be going. So what would normally happen is the Earth and the James Webb will be orbiting, but the James Webb will be like lagging behind. The Earth will be orbiting the Sun quicker than James Webb, but the Earth has an additional source of gravity and it kind of like drags it along, if that makes sense. The gravity from the Earth is what's dragging the James Webb quicker than what it would normally do in its orbit.
Gotcha. And that's so the whole point of that is just to keep it in a relatively stable position where it's not going to have to use too much fuel to stay in place.
Right. It'll just need to because L2, the second Lagrange point where it's going is called it's metastable. So it's not a stable Lagrange point. If you go there, any slight deviation will cause you to drift away from the Lagrange point. It's analogous to if you put a pencil, if you balance a pencil on its point exactly, and you get it to balance, the pencil will be stable and it'll just sit there. But any slight little push will cause the pencil to topple over. We're putting it at that Lagrange point because stuff doesn't tend to collect there. Because at the other Lagrange points, they're stable. And so there's like a little gravity well, essentially, and like little rocks and stuff. They kind of just gather in these little, in those other Lagrange points. And so we're putting it at one where stuff doesn't really collect. But it's still sort of like a stable, metastable. What is today, the 30th? So it's been 5 days since launch. The first 2 weeks are the critical points. That's where everything is opening up, all the sun shields, and the telescope itself is kind of unfolding because we had to fold it in order to get it into space. And there's about 300 or so different things that have to go absolutely right in order for the mission to be a success. And if any one of those goes wrong, it could lead to failure. So
it's not like Hubble where we can send a team out to fix it. It's
right, exactly.
We're never seeing that again.
No. Because if we think about where this L2 point is for the Earth-Sun system, the moon is about, say, 400,000 kilometers away from Earth. This L2 point is 1.5 million kilometers away. So that's about 3 times further out than the moon. We're not going to be sending any astronauts out there to repair that. So it has to go right now. And it currently is. It's in the process, like as we speak right now. It's in the process of unfolding, and it all seems to be going good so far. So fingers crossed.
on the launch, they said they have a feature where they can basically shake it.
Uh-huh.
So as a last resort, if something isn't working, they'll give it a little kick.
It's almost just like hitting it with the hammer, right? Just ding.
Yeah.
That's interesting.
That's their, yeah.
Well, I mean, they have, yeah, I'm sure they have contingency plans and stuff because they really want this to work. I mean, we all do.
And we'll be waiting about 6 months till our first images.
Yeah, our first data.
And then the other thing to keep in mind for everyone who's waiting, like me, we're like eagerly waiting. We didn't get the deep field from Hubble until 14 years after.
Right. So
Hubble
yeah,
launched, so
the first
be patient.
the first few years of James Webb is already spoken for, pretty much agreed upon. We're looking at stuff that we know, like we're looking to confirm certain theories. We're looking to confirm some studies, and just it's been spoken for. I would just say hold on. It'll be interesting no matter what data comes back. I'm sure it'll be fascinating.
It's true. But some of these things like that we really want to find out about, like alien civilizations and things like if we ever get stuff like that, it's gonna be probably a while.
We gotta wait for the galaxy formation cosmologists. I think they have first dibs is looking at early galaxy formation.
Well, I'm really excited for that too. So yeah, this is so cool. I remember talking about James Webb with you in high school. I can't believe it actually.
Dude, it's taken so long. Gosh.
Do you have any final things you'd like to say about this?
I guess after the end of the 2 weeks, whatever podcast that lands on, we can say whether or not it's successful or not.
I will definitely keep updating and such. And as soon as we have something worth looking at, we'll definitely be all over it. All right. Well, thank you guys. And let us know if you have any questions, comments, or yeah. See you guys later.